just in case you're stuck trying to get going on this. What force acts as the centripetal force for an unbanked corner? Friction. Okay, so this is like that net force is the sum of all forces thing. Okay, so for this type of curve, okay, in particular an unbanked curve, our centripetal force is being provided by the force of friction. Okay, that might help you get started. All right, let's have a look at this one. So the givens in this question where we were told the mass of the car, okay, 1,500 kilograms. We were told the radius of the corner was 40.0 meters. And we were told the coefficient of static friction was 0.60. All right, so since it's an unbanked corner, the thing that's keeping us from sliding and thus going around in a circle, okay, is the force of friction. So sum of all forces says that mass times centripetal acceleration, or mv squared over r, equals mu times the normal force. But this is an unbanked corner, so normal force is actually equal to what force? Gravity. Okay, so I can just write mu times m times g. Okay, since I'm trying to solve for the maximum speed, so I'm looking for v, I'm going to multiply both sides by r, divide both sides by m, which is going to cause m to cancel. Okay, and then I'm going to square root everything. So I'll have the square root of the muger, okay, as my formula. That'll be 0.6 times 9.81 times 40 meters. Now, on a question like this is what will sometimes happen, okay? People will look at that, and if I've got, like, let's just say that instead of the significant digits I have here, that all these other ones had more significant digits than 1,500, I'd have people that would give me 4 significant digits. Does the 1,500 count in this question? No, because mass, it canceled. Yeah, it canceled out. So we didn't end up using it, so it doesn't affect the calculation. Okay. So in this situation here, we are going to have the square root of 0.6 times 9.81 times 40 meters. Okay, 15, we only have 2 sig digs because the coefficient of friction only had 2, so 15 meters per second. All right, is that ringing the bell?
If we use mass in the calculations, do we still have to do, can we use it in significant digits?
If it cancels, though, it doesn't matter whether you put it in or not, right? Because it cancels itself off, it isn't actually in there. Its measurement doesn't affect your final answer. Does that sort of make sense? It's very rare that that ever occurs. Okay, any other questions on that one? Okay, what was the other kind of curve we went over? Banked curves, okay. And in a banked curve, right, we have this formula instead, okay? That the tan of theta, and theta is the angle that it's banked at, equals v squared over r times g, okay? And this is another situation where mass cancels, okay? In unbanked curves and banked curves, mass doesn't matter because it cancels out, okay? Gravity affects all things equally, so we've just got little g in there. All right, so any manipulations we make, okay, we make in order to solve, okay, and we are dealing with this situation, the angle of bank and the fact that the object is moving rapidly along them, okay, gives us these forces. This one acts towards the center, so it's Fc. This one offsets gravity, okay, this one is the normal force, and this is the angle of bank, okay, and so we can calculate, that's where we get that formula from. Okay, the steeper the angle of bank, obviously the faster you can go, or the smaller the radius can be. All right, ringing a bell? Okay. Then, those are all unbanked curves, which we just did. And I don't have another bank curve question. So here is what I would like you guys working on here, because I don't want to spend all class on this. Okay. On page 2 of the digital workbook for Unit 3, okay, there are a bunch of questions, but I don't want you to do them all. I only want you to do 2, 4, 6, 9, 13, and 15. So that'll be like two unbanked corners, 1 centripetal acceleration question, and 2 bank curves, and 1 that's just kind of a centripetal force question. Okay? So that's those are the ones I would like you working on here for the next little while. We'll go through any that give us trouble, and then we're gonna move on to artificial gravity, okay, later on in the class today. Okay, so on number 13, okay, we've got a bank curve question. So we're looking for theta, even though it's a plane, it's still a bank curve, okay? And so we have a speed of 115 meters per second, and we have the period this time, okay? So 120 seconds. All right, so what I've got to do first is I've got to use the period to get the radius, because I don't have it, right? And that's kind of the trick to this, is I don't have r, right? If I'm going to use this formula here, tan of theta equals b squared over r times g, I have to have r. So what I'm going to do is I'm going to use this formula here, b equals 2 pi r over t, to get r, because I have v and t. So I'm going to multiply both sides by t, I'm going to divide both sides by 2 pi, and that will give me r. Okay, so we'll have 120 times 115, okay, divided by 2 pi, which does need to be in brackets so that it does it in the right order. All right, so now I've got my radius, 2,196 meters, okay, and now I can manipulate for the banking angle, which is simply taking tan over to the other side. Okay, so inverse tan of 115 squared divided by the 2,196 with all the decimals, okay, times pi, or sorry, times g, 9.81. Okay, so if I plug all of that in, 115 squared divided by, and then the bottom does have to be in brackets, okay, that number times 9.81. Okay, so we get, oh, I forgot the inverse tan that. Inverse tan of that number. Okay, and we get 31.5 degrees as our bank. Okay. Any other ones, guys? Okay, then we are going to talk about artificial gravity. Now, how many people have seen the movie The Martian? Okay, how many people have read the book? Read the book, it's better. Like, I mean, and I don't mean like a little bit better. I mean like it's way better. Okay? I always tell this because I actually got that book for free on Amazon when it was first self-published by Andy Weir. Okay? And I was like, holy crap, this is the greatest deal ever. Okay? This was free, and it was awesome. Okay? So, in The Martian, their ship has part of its structure that spins. Okay? That spinning structure of the ship, okay, is generating artificial gravity in the right way. Okay? Unfortunately, with a lot of older science fiction, you know, like Star Wars and Star Trek, artificial gravity was just this magic thing that everybody had. Okay? And there wasn't any reason for it. It was just there because it was convenient, because, well, you didn't want everybody floating around on the ship because that's expensive to film and make look realistic. Okay? So they just said the artificial gravity is on, and for some reason nothing ever affected that. Okay? Like there was basically no situation where the ship was about to be destroyed where the artificial gravity went off. Okay? Well, it can happen pretty easily if you're generating it the way we understand, which is not by magic. Okay? And that is by using centripetal force. If you have any part of the ship that is a spinning drum, okay, and the people are on the inside, it only works on the inside, okay, then artificial gravity will be generated. It's not real gravity. It feels like it as long as you're on the inside layer of the artificial drum. If you're anywhere else, it doesn't work. Okay, like if you're, you know, climbing a ladder, you'll get lighter and lighter and lighter as you climb the ladder towards the center of the drum, because your radius will decrease. And once you're in the middle, the radius will be 0, and there will be a tube along the middle of that drum where there's no gravity. Okay, so you got to kind of be prepared for little things like that. And if anyone were to, you know, shut off the artificial gravity, like stop the spinning, everything is going to go floating around. Okay? In addition to the fact that it's moving in a circle. If you start slowing that down, everything has inertia and it's going to want to slide. It's going to want to keep doing what it was doing before. So turning it off is something you don't want to just, oh, we'll just flick the switch and shut that off for now. You're going to have a big mess to clean up after that. Okay? Especially if it stops suddenly. Right? Imagine you're just on the inside of this thing and something stops. Well, you keep going and you're going to face plant into the floor.
Would you die?
Oh, you wouldn't die. You just face plant and then float away, unconscious probably, and wouldn't look very dignified. So, obviously in movies, the purpose of having artificial gravity is to, well, save money. It's really expensive to film in zero gravity. And you don't go into space to do it. Okay? Most movies involving artificial gravity are actually filmed in the zero gravity trainer. Okay? Either, well, sometimes they film it in Russia, but not now. Sometimes they use NASA's Vomit Comet. That's what the astronauts call it, the Vomit Comet. Because it's a 747 that's been all hollowed out, and it just goes up and down and generates artificial gravity about 30 seconds at a time. And in fact, if you've ever seen Apollo 13, all of the zero gravity shots in Apollo 13 were filmed in a set built inside of a plane doing exactly that. Okay, we'll talk a little bit more about that when we get to vertical circular motion. Okay, but the main idea behind wanting to generate artificial gravity is how bad zero gravity is for the human body. It's really bad. Okay, most of Chris Hadfield's research, a Canadian astronaut, was based around the long-term effects of being in zero gravity. Okay, and there's lots of really bad stuff that happens to the human body because we didn't evolve in zero gravity. We evolved in a gravity environment, and a lot of our sensory functioning is based around having gravity, especially balance. Okay? When you initially get into zero gravity, the first couple of days, you're just green, just sick, because your body is constantly telling you that you're spinning, you're falling, you're upside down, you're right side up, you're sideways, okay? Because our balance center relies on some stuff in the middle here, okay? And there's these little, they call them hair cells because they kind of look like that, but they're not actually hair, okay? And when you turn your head, there's like little granules that can shift down because of gravity, and they tell your body you're leaning, and your body automatically tenses the muscles on the other side to keep your balance. Okay, and these things can get messed up, if you're doing like the dizzy bat race, or something like that that gets you really dizzy, okay, those things are going around, they get overstimulated, and you're like, oh god, then you feel dizzy and gross. Well, in zero gravity, those things are constantly screaming at the brain, okay? It's like that car alarm that, it's always going off, okay, and it's really, really annoying. It's like that, and it's just always screaming at the brain. You're upside down, you're falling, you're turning, you're falling, you're upside down, and and the brain finally just goes, shut up. And it just totally stops listening to the balance center in your brain. Okay? Instead, it says, talk to the eyes. The eyes can tell us if we're upside down or right side up. And so the body will slowly shift to relying on the eyes for balance, which works great in zero gravity. But it's really bad in real gravity. So let's say you fly to Mars in a ship not equipped with a gravity generator. And when you get to Mars, you've been in zero G for 6 months. Okay? You've lost some muscle mass, okay? Maybe we'll talk about some of the other things that have happened, but the big thing is your body is shifted to relying on your eyes for balance. Okay? Now, you land on Mars and you're about to do the Neil Armstrong thing, but for Mars, okay? Leave the first footprints on Mars. And you get to the edge of the ladder and you're looking down and your brain is listening to your eyes about your body position, and you do this and the body goes, you're falling! And your body tenses, and then you actually fall down the stairs, and you leave the first faceplate print on the surface of Mars in a very undignified way. Okay? Possibly breaking your faceplate and becoming the first corpse on the surface of Mars, which would also be very bad.
Is Mars gravity greater or less?
Less, 1/3 is what it is here, which is something they don't do a good job of showing in The Martian. Okay, like they don't do a good job of showing that he's actually way lighter than he should be, right? A lot of the work he does obviously on Earth where they filmed the movie, but you can tell it's Earth because it should have been so much easier for him to do.
Right.
Yeah. Okay? Like when he tried to jump on the roof of the rover to break open the hole, right? That would so not have worked on Mars. They did it on Earth, and they're like, oh, just do this on Mars. What? 1/3 gravity. He's not gonna break that, right? Like, he's not heavy enough. So, there's all kinds of things to consider, okay, when we're talking about the effects of zero gravity on the body, okay? First thing, zero gravity on the body, balance. Second thing, muscle mass, okay? And that's not just your skeletal muscles, right? They've got an exercise machine on the International Space Station. I'll show you a video of them using it. It's kind of like a Bowflex, because obviously you don't bring weights, right, up into space. It's really expensive to move weight, and they're useless in space. So you don't want to bring those. So it's a resistance machine. And they can keep their muscles in pretty good shape. They can do some cardio. They have a special treadmill, okay, that they have to be like tied to by bungee cords, because running on a treadmill in zero gravity looks pretty funny. One step and you float away, okay, unless you're tied down to it. So they got this like harness that they wear and bungee cords them onto the thing, and they can run a little bit. Okay, stationary bike as well, same thing. They have to be tied to it basically. So they can keep their cardio up a little bit, but it's only a little bit each day. I mean, you got to get other work done. You can't be on the treadmill or the bike all day. So your heart and your lungs get weak because they're pumping blood that doesn't weigh anything, and they're used to pumping blood that does. Okay? And so they get weak. And it's a big concern when you come back to Earth, if you've been in zero gravity for a long time, that your heart and lungs may not be capable of getting the job done when you return to gravity. Okay? This doesn't happen most of the time because they've got all this stuff going on, but back when the Soviet Union collapsed, there were astronauts up on their space station called Mir, and they got stranded there because the Soviet Union had collapsed. They had no economy, and they couldn't send any flights up to get them. Of course, the Americans were like, we'll go. You'll go look at all your stuff, but we'll rescue your astronauts. We'll do that for you. And they're like, hell no. Okay, you're not going up there. It's Russian soil. You can't go on our space station. So they let them send supplies, but not go. So these guys stayed up there for, I can't remember how long. It was a really long time. Okay, longer than anyone had ever been in space before. And when they came back, they almost died. Like, they had to be put on like respirator, like ventilators and stuff, because the muscles that control your breathing, the ones that lift your rib cage up so that you can breathe in, were so weak that these guys could barely breathe on Earth. Okay, so it was really bad. You don't want to be in zero gravity long term because your body gets weak. Okay, now when your muscles start to break down, your body recycles them. Okay, but it's also the same with your bones. Okay, if you're not exposing your bones to gravity, they'll also get weak. Okay, and your body will start to recycle them, and you'll end up feeling like essentially having bones like an elderly person. Okay, you guys have heard of osteoporosis? Okay, the only way to kind of treat osteoporosis is to do weight-bearing exercise. They usually tell people go for walks, lift small amounts of weight, with the little tiny dumbbells and things like that, so that you cause little microfractures in your bones that heal and make the bones stronger. Okay? Someone who like breaks bricks and boards and stuff, they get really dense bones in those areas because they're constantly creating lots of microfractures. So every time you break a bone, once it heals, it's going to heal back stronger. Okay, so these little microfractures make your bones more dense. That's what they want to do for someone who has osteoporosis. Well, if you're in space, there's not much you can do, okay, to keep your bones strong. Work out a little bit, but it's not the same as having gravity constantly trying to break them down. Okay, so they get weak, so you can get that. When the bones break down, calcium ends up in the blood, and the kidneys have to filter it. You get too much calcium in the blood, kidneys can form kidney stones, which on Earth are painful and inconvenient. Okay, and usually cause urinary tract infections and things like that. Well, if you're a few million miles from the nearest hospital, a kidney stone is a much more serious medical issue. Okay, and so there's all kinds of things to consider with that kind of stuff. Okay, loss of blood plasma. Okay, and of course, if you're in space, you're exposed to more radiation. Your face also gets really puffy when you first go into space because all the fluid redistributes throughout your whole body. In fact, astronauts often complain of being quite arthritic the first little while because most of the time the fluid just goes down because of gravity. But in zero gravity, it goes everywhere, and so you get swelling in your hands and swelling in your face. In fact, sometimes it looks like they've gone a few rounds, okay, and they're like really, really puffy in the face.
When you're drinking water in space, how does it go how does it go down your, would it not?
Peristalsis. So the muscle contractions, right?
Right.
Like you can still drink up, like if you
Okay.
did a handstand, you'd still
Right.
be able to drink water. It's just not, it's not as easy.
Right.
Yeah. You certainly wouldn't be like chugging,
No.
yeah, in space, because it's not gonna, you know, that relies a lot on gravity. Lots of things rely on gravity. That's what I'm gonna show you some of the videos of. Here's how we deal with this problem, here's how we deal with this problem, okay? Now, here's one to think about, because they don't talk much about this one ever. How do you go to the bathroom? We rely on gravity for going to the bathroom, big time. Okay, everything falls away from us on Earth, that's good. Okay, in zero gravity, that's not what happens. Okay, so there's a special hose, okay, for urine, special hose, and everybody has their own end. Okay, they learned that one with the Apollo missions. If you've seen the Apollo 13 movie, okay? Yeah, they all got gonorrhea from the same tube because one of them, yeah. And then, so everyone gets their own tube, but that's for urine. Poop is different. Okay, so it's a little windy, they say, in the space john, right? Because essentially what they do is they open a little bit to space, so the air is constantly rushing through, and it creates a pulling so that the poop doesn't float. Okay, and it gets kind of sucked into the waste receptacle, and then yeah, so it's very different to use the bathroom in space. And then every once in a while they have to jettison the waste receptacle. Yeah. So it burns up in the atmosphere. At least that's what they tell us. Hopefully none of them have made it all the way back to the ground. That'd be the grossest meteor ever. Okay, so those are some of the things that can go on, but we just take so much for granted in gravity. And they get really used to zero gravity when they're up there. When they come back down, they have to make a lot of adjustments. In fact, one of the things is when they first get out and they're trying to walk around, they usually have one person on each arm, making sure they don't fall. Okay? Because again, their balance has shifted back to their eyes. Okay? And so when they're first coming back to Earth, that's still the way it works. If they're walking in a straight line and somebody says, "Hey, Chris," and they look, they'll fall. Okay? Because they're like, "What?" And their brain will go, "No, you're falling," and boom, down you go. Okay? Because their eyes are what's telling their brain where they are. As soon as you turn your head and do this, your brain says, "Okay, now you're oriented like this," and tenses the wrong muscles, and down you go. Okay? So it takes a little while for the brain to revert back to listening to the right balance center and keeping them on their feet. Okay.